everyone. In this video, I'm going to share our work, condition-aware neural network for controlled image generation. Large-scale diffusion models have demonstrated astounding capacity in synthesizing photorealistic images. To convert these models into productive tools for us, we need to add control. Instead of letting the model randomly generate data samples, we want the diffusion model to follow our prompts, like the text, class label, etc. Condition-aware neural network, or in short CAN, is a new mechanism for this problem. The core idea of CAN is to add control by adaptively manipulating the weight of diffusion models. This is achieved by introducing an extra conditional weight generation module. This module takes the condition embedding as the input and outputs the conditional weight to adapt the base weight. Prior to CAN, there are two mainstream methods. The first is using attention. For example, we can use the cross attention with the image feature as the query and the condition feature as the key and value to fuse the feature. Alternatively, we can also directly concat image feature and the condition feature along the token dimension. Then we can use the self-attention for feature fusion. The second is adaptive normalization, which adaptively scales and shifts the image feature based on the condition embedding, which is a method used in diffusion transformer. The main difference between CAN and prior conditional control methods is that prior methods adds condition through adapting the feature. In contrast, CAN adds conditions by changing the weight. So now the question is, why adapting the weight is a valid mechanism for control? To illustrate this, here we consider a simple case. Class conditioned image generation with two classes, like one is cat and the other is castle. For this simple problem, one solution is to just maintain two expert models. So we have one expert model for cat image generation and the other expert model for castle image generation. Then we can determine which model to use based on the input prompt using the route. The advantage of this solution is that it can avoid negative transfer between different expert models. The cat image distribution is different from the castle image distribution. Therefore, directly sharing the weight may hurt the overall performance, and using this approach, we can avoid this. However, in practice, this approach is infeasible because it is computationally prohibitive to train and maintain an expert model for each case. Therefore, we use CAN as an efficient instantiation of this idea. Instead of explicitly having different expert models, we use a weight generation module to enable weight difference. We apply CAN to existing diffusion transformers, including DIT and UVIT, to justify the effectiveness. On ImageNet, CAN can consistently delivers lower FID and higher clip score for all variants. Here is the direct comparison between CAN and prior conditional control methods. We have two interesting findings. First, we find that using CAN alone can work as an effective conditional control method, outperforming both adaptive normalization and attention. Second, we find that CAN can be combined with other conditional control methods to achieve better results. Like on DIT, we find CAN combined with the adaptive normalization achieves the best results. Apart from applying CAN to existing diffusion transformers, we also apply CAN to efficient VIT that is more friendly for high-resolution vision. The key design of efficient VIT is to replace the heavy soft-like attention in transformer with lightweight value linear attention to break the efficiency bottleneck. However, there is no free lunch. Value linear attention cannot produce sharp distributions due to the lack of nonlinear activation function, making it bad at capturing local information. In efficient VIT, we introduce a simple but effective solution to address this. Since linear attention is not good at local feature extraction, we enhance it with convolution that has shown good capacity in capturing local information. In this way, we combine the best of both worlds, having linear attention to focus on contextual information and letting the convolution to focus on local information. Combining CAN and efficient VIT, we get a new family of diffusion transformers called CAT. Here we show our final results on class conditioned image generation on ImageNet. CAT achieves a lower FID than DIT XL with 52 times less computational cost. It shows the potential using CAT for edge AI applications. In addition to class conditioned image generation, we also test our models on text-to-image generation using the COCO dataset. Compared to UVIT, CAT can match the performance with 6 times less computational cost. That's all. Thanks for listening.